So as we have already seen in the performance analysis of digital modulation schemes, we have four factors that we need to consider so that we can determine which amongst the many schemes are best suited for a given task or for a given function. So we have looked at power spectral density, and now you're going to be looking at the average probability of signal error, which is sometimes referred to as the bit energy to noise density ratio. After that, we look at bandwidth efficiency and the channel bandwidth requirements, as well as the power requirements of a given modulation scheme. So right now, we start with the average probability of signal error. The probability of error is going to be considered where we are saying we have received a signal at the optimum receiver, and the signal that we have received has passed through a AWGN channel, that is additive white Gaussian noise channel. That means that if we had sent x of t, we are going to receive at this point x of t mixed up with some additive noise n of t. And remember that at the transmitter we are setting carrier modulated signal, which may be ASK, BPSK, or FSK, and there are many variants of this as we have already seen. And at the receiver, what we are going to do, we are considering first and foremost a coherent receiver, and the coherent receiver will first and foremost remove the carrier signal, if you can use that word, so that we are left with the baseband pulses, which are often either NRZ or Gaussian, as we have seen in the past. So NRZ might be pulses that are going positive going pulse representing a 1, or negative going pulse representing a 0, or vice versa, of just a positive going pulse, and then the absence of that pulse represents a 0. So once we are able to remove the carrier signal that was modulated by these pulses, we are now going to end up with pulses that are of that shape, or sometimes that are barely the size that we expect them to be, because the noise, while we expect that probably a positive 5 volts supposed to go to reach at that point, then we realize that because of noise, the signal has been degraded, and therefore it is not yet reaching the maximum or the optimal value that we expected to reach. So if that be the case, this is the result of the noise that the signal has gone through. And for that reason, we want to be able to determine whether this pulse represents a binary 0 or a binary 1. So if we are using a modulation scheme that uses positive pulse for a 1 and 0 pulse for a 0, and we have received probably a pulse of this size, that means there is likelihood like that this signal or this pulse is as a result of noise only, and not a positive pulse was sent. How now do we determine whether this signal is a positive 1 or a negative 0? We say that the pulse that we are receiving is likely going to be represented mathematically as this plus noise. That might be representing symbol 1, and or x2 of t plus noise. This might be representing symbol 0. But now this noise might cause us to receive this kind of signal. What we want to be able to do is to determine what is the threshold value below which we classify a signal to be a binary 1 or binary 0. So what we normally do is we normally get a threshold or a decision boundary between the two extremes. So if this is our positive pulse and this is our 0 pulse, if a signal is received that is of a voltage within this range, then we say that that is going to be classified as binary 0. While if we receive a pulse within that range, that for instance, that is a pulse that we have received, then we say that this is going to be classified as binary 1. If we receive a pulse that looks like that, it is within our 0 binary limit or range, then we classify this pulse to represent 0 and this one to represent 1. So mathematically, how do we do that? If we know this is representing x1 of t and this is representing x2 of t, remember x2 of t represents the binary 0, then we can say that the midpoint between them can be found by just saying x1 of t plus x2 of t divided by 2. This gives us the average value here, or the midpoint value there. And this now is classified as our decision boundary. This is our decision boundary, or a threshold value that now we will use to determine what is the probability that a signal will be above or below the decision boundary. It is meant, or it was meant to be vice versa. For instance, say we have received a pulse of that size, and it is slightly above our decision boundary, and let's say that this pulse was actually a zero pulse. So we are saying that it has gone above the range for classifying it as zero. So this pulse is going to be received in error. And therefore, there is some probability of receiving some pulses in error. For in actual sense, they represent the figure that we know it was not meant to receive. So how do we determine what the value that will be in error? What is the probability of receiving some bits in error? And this is very simple. The value of this signal we can classify to be x. So we are saying that probability that x is in error can be found to be when x is bigger than our range x1 plus x2 divided by 2 minus our lower limit, which is x2. Remember that x2 may not always be 0, it might be negative 5. So this formula now says that when our value of received pulse is bigger than a given range, and yet suppose we know it should be representing our x2, then we classify that to be the probability of error. And this is this can be simplified further to say that probability of error of x can be found to be when x is bigger than or equals to x plus x over 2 minus, if we put the 2 to be the same base, then we can say this x1 plus x2, and this becomes 2 over 2. So means minus 2x2. And when you simplify this further, you get that probability of error of x is going to be when x is bigger than or equals to x minus x1 minus x2 over 2. That is a very significant limit, that when our x is bigger than this value, then we are saying that that x is going to be in error. And now we remember that this error is caused by Gaussian noise, because we are saying that the channel is additive white Gaussian noise channel. And the kind of noise that is experienced in that kind of a channel is normally characterized by n of t, and n of t is said to have probability distribution function pdf, which may be represented by 1 over sigma 2 pi e minus n squared of t divided by 2 sigma squared. And now with this pdf, we can be able to characterize that what is the level of a given noise in that channel. And graphically, we can represent that noise to be normal. This is the normal distribution curve, and the normal distribution curve at zero mean. So this is the curve that is represented by this vision, and this is the one saying that this is our how we can represent our Gaussian noise graphically, or with this expression here. The PDF may be represented by that. So from this curve, we are saying that when this is the value of x, and this is our f of x, and therefore we are saying that when x is bigger than x1 minus x2 over 2, this is the error that we are experiencing. And so this side of this curve is the one that is going to characterize our noise. And therefore, if we wanted to find the total probability of that we are likely to receive our signal in our x to be in error, then we need to find the area under this curve, that section. And because this is a two-tailed distribution curve, we definitely know that this side is equivalent to what we have on this side, and therefore the area under this curve is going to be equivalent to C, or cumulative distribution function. And how do we find the cumulative distribution function? We know that we are able to find the area under this curve by simply integrating from this point x1 minus x2 divided by 2 to infinity. This goes all the way to infinity, and then we integrate our PDF, which is 1 over sigma 2 pi e minus nt squared divided by 2 sigma squared with respect to nt. So our function now here is nt. So we want to find the area under this curve, and this area, the area under this curve is going to be given by the integral of our function, our PDF function, with respect to nt. And we may do a very simple substitution here and say that nt squared over 2 sigma squared, you can say let it to be equals to, or let this to be equals to y squared, so that we can say that y can be represented by nt over sigma root 2. And therefore, if we want to do further integration, we want to find the dy in terms of nt, you can see that this is equivalent to dnt over sigma root 2. And therefore, we want to replace this one mathematically and say that dnt is equivalent to sigma 2 dy. So for us now to replace this one, so that to be the function that we can be able to perform the integration, we are going to say that our limits are going to change definitely, because we have changed our integral. So we are going to say that when nt is equals to x1 minus x2 divided by 2, then our y becomes what? Remember, our y is represented by this one. So we are going to simply say equals to x1 minus x2 all over 2 sigma root 2. I've just combined this equation with this one. And similarly, when nt is equal to infinity here, our noise is approaching infinity, then our y will definitely become infinity. So then our CDF, our cumulative distribution function, which is our probability of error, PE, is going to be given by this value of y, x1 minus x2 all over 2 root 2 sigma 1 divided by sigma root 2 pi exponent. Now this whole of this one has become our y minus y squared, and our dnt changed to become this value. Remember, this is what we did here. You say dnt is equal to sigma root 2 dy. Therefore, you can divide this by this 2 by root 2. Therefore, you are left with root pi. So our PDF, or sorry, our CDF, or probability of error, that x is in error, it simply becomes integral of x1 minus x2 all over 2 root 2 sigma 1 over root of pi exponent of minus y squared dy. There is something we know about error function that says if we introduce, so I want to move this around. So I've just moved the constant outside the integral, and now with this form, we just need to introduce one more concept here: pi by 2 divided by 2. This integral is known as the complementary error function, and we can now say that this is going to 1 over 2, this half, then ERFC, and the function for the variable that goes to the error function is this lower integral here, and therefore we are saying that x1 minus x2 divided by 2 root 2 sigma. And this now is our expression for probability of error. We normally say that if we have a digital modulation scheme, maybe ASK, PSK, or FSK, and we are transmitting the two binary symbols, x1, of course this is a function of t, and x2 of t, each with 2 levels, then we can be able to obtain the probability that some bits or some signals might be received in error due to the AWGN, or additive white Gaussian noise. So the bigger this distance between the two signals, smaller the probability of error. We say that the probability of error, or the ERFC, or the complementary error function, the decreasing function, such that when this gap increases or when this value increases, the probability of error decreases, and vice versa. So that our preference is that when the difference between x1 and x2, this should be big, always be big, or should be big enough to reduce the probability of error. When we have a very small distance between the two levels of the received signals, then we are likely to have we are going to have higher probability of error. So we will be using this function. We will not be deriving it again. We will be using this function to find out what is the probability of error in ASK or BESK, BPSK or BFSK, and other coherent modulation schemes. We will find out that it is sometimes not possible to find out the probability of error when using this method when our modulation scheme is not coherent, and number two, when probably it has multiple or more than two levels like we have here. So for that reason, we are going to find another method. But for the basic modulation schemes like BSK, BPSK, or BFSK, then this is going to be our standard formula for finding the probability of error.